Hi everyone, my name is Marko and welcome to my talk. So, Demystifying memory, so a practical tutorial on managing and optimizing memory in Zephyr. So, this is going to be a talk purely from Zephyr application developer perspective, not from the maintainer perspective. It's going to be based on the project that we did with a client that we ran into some memory issues, and we were looking hard and long into what can be done to lower the flash consumption, to lower the RAM consumption, and we learned a few tricks, I guess, or we found about things, and yeah, I thought it was a good idea to share this as a talk. A little bit about me. I'm an embedded system engineer by profession, electronics engineer by education. At our company, I went through, let's say, through the whole hardware stack from the PCB designer to the firmware engineer. I worked on several different products from several different industries. And besides the primary focus as a firmware engineer, my secondary focus was also in-house tooling, setting up developer environments, CI, and processes, and etc. I work for IRNAS, so we are a small company, about 18 people, and we essentially do kind of a rapid prototyping first phase of a product and bring it all the way up so it's suitable for mass production. Yeah, so we do a lot of stuff. Okay, so main motivation for this talk. So very, very vaguely said, so we were developing an IoT device that was sending data over the Wi-Fi. Our key components on the PCB were NRF53, NRF7002, and external flash chips. Those are like the main focus points of this talk. It had a UI, so a e-ink display and just 2 buttons, so nothing fancy. And on the cloud side, it was decided to use the Azure IoT Hub as a service. So those who are not so familiar with that, it's essentially MQTT with additional layer of application logic, which provides you a way to sense telemetry data, a way to have like an abstract device twin interface, so some kind of a mirrored state between the device and the server. You can directly send messages which are supposed to be fast, but all in all, you are really just sending JSON objects, strings from the device, and you're also receiving them. The provisioning of the Wi-Fi credentials. So we are using the Wi-Fi to connect to connect the device to the network. We have to provision the credentials. That will be done through the BLE. LVGL would be used to render the graphics, and we were expected to use the external flash chip to store the assets and second image slot. And we kind of, based on what are the features here, we kind of already anticipated that there will be some code relocation and there will be a need to use execute in place. Because we assume that probably the flash portion of the chip is not going to be enough. So we said, okay, we want to find out as soon as possible, like how wrong we are about our assumptions. So we said, okay, we want to find a sample that has most of those features and see where we are with the memory consumption. So first good approximation of that was the Azure IoT Hub sample in the NRF subtree, which only uses the Azure. It doesn't use the Bluetooth. It doesn't use LVGL, but it does contain M2 boot. So already the external partition is on the second slot. The second image slot is already an external partition, and yeah, that was like the first start. And this is the memory report out of the box. So if you notice, so I don't have a. Oh, I do. Okay, so if you notice, so those who are maybe working with Nordic, with Nordic's NCS probably are familiar with these 3 sets of images. So one for the M2 boot, one for the TFN, and one for the application itself. And the stuff that was starting to slightly worry us was this bottom part. So after just running the application as it was, we basically had, for example, only 61 kilobytes of flash available for application logic, or the rest of the logic, let's call it like that, and 69 kilobytes of RAM available. So without us writing any business logic code, or even using LVGL or the other stuff, this is what we were left with, or this is what we were starting with. And of course, this sample changed through the time when we were working with the NCS. At the beginning, the LTO was not enabled on 3.1, which came, I think, a few weeks out, which came out a few weeks ago. LTO was already enabled. So this was essentially the setup that you would have. So this was kind of our motivation, and later I'm going to present a few ways that you can determine, okay, what do I need to tune and what can I change. But for now, let's talk about the basics. So really, really quickly, flash and RAM. In this context, I'm talking about memory regions. I'm not talking about specific memory device technologies. So flash, read-only memory, it's non-volatile, the data will be contained after power loss, and it stores program code, read-only data, and initial values for the initialized data. RAM memory, read-write memory, it's volatile, it loses contents on the power loss, and it holds initialized data, zero initialized data, dynamic memory, and stacks. Few things that you need to point out, like the zero initialized data, so BSS, does not consume any space in the flash. So if you configure your, usually your stacks are stored there, so this is not the size that you are paying in the flash space. But for the initialized data, you're paying this price both in the flash and both in the RAM, because at the boot, this section is copied into the RAM. So if you can, make sure that data that you're not changing is marked as const, because then it's only going to be put into the flash and not the RAM itself. And yeah, on the right side, you can see like an annotated hello world example of this style. Like every single variable is in a specific section, and they're named, so it's very clear what is going on. Yeah, so data section, flash to RAM at startup, read-only data section only in flash, BSS section, it just lives there. It just, let's say, appears in the RAM, but it's not actually in the flash. This is kind of becomes important when you're trying to figure out where stuff is in the Zephyr and how actually will that impact your memory consumption. So memory management in Zephyr. So two very common, but there are not only those two, but there are two very common memory management techniques are K-heap and memory slabs. So if you see K-heap, that is basically thread-safe heap allocator with timeout arguments, and it's built on top of a sysheap. So sysheap is just memory allocator without any synchronization primitives. And memory slabs, these are fixed size blocks. You say how many blocks you want to have and how big they are, and you define this at the compile time. So on the right side, you can see like how would you put this into how would you use this in the code, and those two concrete examples are specifically the first one is the one for the system heap. So system heap is just a K-heap, but actually that's like this one exposes libc-like API. So you get a K-malloc and K-free. And this is also something, if you have to deal with a heap memory on the Zephyr application, in your Zephyr application, this is what you're supposed to use. So this one, not the one provided by the libc. I will briefly say afterwards why. And its size is controlled by the heap mempool size kconfig. But essentially, it's just a wrapper around the kconfig. So if you have those two macros in your code, Later, very simplified, they get expanded to something like this. So I'm really omitting a lot of the information here because there's a lot of attributes there that they put where those, which dictate where those symbols get put. But very simplistically said, the macro will resolve into an array with the size of the size that you passed, and some data structure that references that array. So if you want to optimize something, this is the variable, this is the symbol that you're optimizing. So you figure out where's the variable, and then you figure out, okay, where is what is controlling this size. Similarly, for the same goes for the memslabs. So it's just an array with a certain size and a data structure that references it. Again, a lot of things are omitted here, but this is what you generally get. So there's a convention because of the macros. Whatever variable that whatever name that you're going to put inside, you're going to get a prefix in front of it, and that's a way for you to know where to find something. One really important thing is that the way the Zephyr is by default doing this, and what is a little bit different from maybe heap memory in other systems, is that RAM usage, because memory heap allocators are allocating from this space is already accounted for in the memory report. So if you are only using the kmalloc and kfree, and memory report says that that your application is going to use up 80% of the RAM, it's going to consume up to 80% of the RAM. It's not going to be like 90, 99 or something like this. So you can really know, okay, this is exactly what I use, and if you fail to allocate memory, you know that you have to change that size. Like I said, there is a caveat. So why kmalloc is, one of the things why kmalloc is suggested instead of the malloc is that where the malloc allocates from depends on the choice of the libc. I think new lib allocates from at the end of the RAM section to the whatever is left of the RAM data section in the RAM. Yeah. So what are some useful tools and approaches for memory analysis? So those should be, people who ever did that, they should be familiar with that. So this is already, Zephyr already provides nice tools for that. So we have our ROM report, RAM report. It shows a data tree-like structure with all the folders and all the files and all the variables, symbols, and their sizes and their sections, where are they placed. Now, if you're using sysbuild, you have to add a flag where you say, okay, I'm looking at a specific sample, or I'm looking at a specific app inside of the sysbuild that I want to run this on. The other two useful commands come from the binutils package. So nm and address to line. So nm for the use case where you have a name of a symbol and you want to find its type and location. So you use nm, you point it to the binary, and it will output a lot of symbols, and you can just grab through it and find the stuff that you need. The address to line, you have your address, and you want to figure out now where is this symbol located inside of the source code, because that's also not the most of the time that's not the easiest task to do with just grabbing through the Zephyr. The next one, which is very, very visual and very useful, is the pun cover. So this Zephyr has an integration for that. It's an external tool, and you basically it works like that. You build your binary, and you run a west-build-t pun cover command, and you get a web server or web GUI through which you can click through and look at the code. And there you can see the code size, you can see variable size. If you have a special kconfig symbol enabled, you can also see worst case stack analysis up to the point where it's clear to the pun cover what kind of functions are you using, because as you know, probably there are a lot of callbacks in the twister, and you cannot always know for sure what kind of a call stack the function will have that you're calling. So there's a small asterisk with that. It has this remarks column here, which says basically if it says X module, function is called from another file. If it says float, function will eventually call the floating point function. Although it's not really on the punk cover page. It's not really documented what exactly those two columns show. But if you look through the code, it's basically code is a .text section, and static is data, row data, and BSS. So whatever appears on the right side, you also have to first figure out with, for example, binutils tools, am I looking at the initialized data? Am I looking at the read-only data? Because then you know what it's impacting. Is it impacting both flash? Is it impacted only RAM or only flash? Yeah. Yeah. So another useful tool, thread analyzer. This one is really easy to set up. Essentially, I think if you just put the first symbol, and maybe if you just enable it, maybe put config thread name, you can already use it in the shell, and this is some kind of output that you're gonna get. The most useful, at least for me, the most useful thing is the maximum watermark or maximum usage of the stack space for each thread. So, and this is shown here on the right side with the % signs, because essentially thread analyze where okay, this is the maximum as you ever got, and you can then decide, okay, how much I want to cut away the rest of the stuff. So heap and memory slab analysis. So this one is a little bit different. So thread analyzer knows for each thread that's in the Zephyr, and therefore it can enumerate them, it can show some data about them, but that it's not true for the heaps. So as a developer, you need to know where the heaps are, or more specifically, what are those names, and you have to then essentially export them and use some statistics functions on them to extract the data. So specifically for the heap, actually for the system heap, this is already done. You can just use this symbol, and you're gonna get the API, you're gonna get a shell, and that's gonna work. But if you have some other heaps, which there are many, you can just write extern struct name of the heap, and you're gonna get access to it, and you can use the same function as you would use for the sysheap on the kheap. Just lock it with the primitive, pass it in, get the stats out, and unlock it. Same thing, very similar thing with the memory slab. Yeah, just get access to it, and then put it in the and then access the info member, and you will get some data here. By default, you don't know what is the maximum used. This because for the basic operation, this is not needed. So there's a kconfig that you're supposed to enable to get the maximum usage. And again, you know the maximum used usage. If you know that it's true for all the time, you can then adjust the size of the memory slab. Yeah. So this one, that one was a little bit interesting to figure out. So those who have used some Wi-Fi applications probably know that Embed TLS uses a lot of heap. What you might not have dived into is that Embed TLS does not use kheap or any heap from the Zephyr. It has its own, it has its own memory allocator, and the Zephyr integration code provides the buffer. So if you look into the Zephyr modules, embed TLS in its code, it's going to be there. The array is going to be defined there, but it's just passed as a pointer to the embed TLS, and embed TLS does the allocation. So luckily enough for us, there is a way to the embed TLS already implements basically the statistics, so you can figure out what is the maximum used setup. So if you enable those four things there, you're gonna get that. but that is only true, I think it's only true for the Zephyr setup. So for the NRF setup, or usually with NRF with the TFM, there are 2 additional things that you need to do currently. For some reason, the last symbol when you enable it will also complain, or it will put an error about the libc not finding the end of the RAM space in the TFM, the end of the heap space in the TFM, because TFM by default does not have any heap. So one of those 2 symbols, so config debug or TFM CMake build type release with the deb info, will add a little bit of heap, just enough for the build to pass, and you can then use the shell command on it to get it. I would recommend running this first one, because I think this first one is the one that really modifies just the TFM significantly. The other one would modify naturally the whole Zephyr application. And yeah, the last one is, since this shell is not readily available in the NCS code, you have to make sure that you compile it inside of this particular file. So network stack. This is a very complicated topic, and I will not say that I completely fully understand everything about this. There are a lot of knobs to turn, so to say, in this, and this is it's a constant battle between how many packets you want to have, what kind of a throughput you want to have, and what kind of a memory consumption you want to have. But really, roughly saying is, the net packets and the net buffs are essentially are limited resources that you have available. So if you have network packets, that's and you're only using 2, you can remove the other 2. So the question is then, of course, like to figure out how many do you need, how many does your application need for your specific use case, and same goes for the net buffs. Now, the net buffs by themselves can either hold a fixed amount of data. So this is the default that the rest of the Zephyr uses. The default is 128 bytes. Or they can be variable sized. So meaning once a buffer is created, it will also allocate some amount of memory from some memory pool. And you can, of course, define the size of the data pool. And yeah, and this is something that you can optimize based on your application needs. Why I'm talking about this? So this is what NRF 1000 drivers use by default. So this is the more optimized space. This optimizes the space usage. It does not use. So for example, if the net buff will only use half of the packet, it would not allocate. It will not allocate 128 bytes, but only 64. And for that reason, there are a few variables here that you can look into. So the first 2 control the size of that heap. And here's contain the heap, and this is the kconfig to control it. The last 2 are actually memory pools for the NRF 7000 communication. This changed some NCS versions ago. Initially, if I remember correctly, this was just done in the main heap, but then this was split into data in control planes, and every Nordic sample with the 7000 will set these to some values, and this depends on, are you doing just the scanning, are you connecting, and again, yeah, you can optimize this towards your needs, but you have to watch them. So you can use the previous approach and be like, okay, if this consumes maximum 30K, let's put it, I don't know, 35, something like this. And yeah, also something to add, there are, for the network packets, of course, there are the RX, and you can configure the application differently for the RX path and for the TX path. So depending on if you're mostly sending data, you might not care. You might not give a lot of memory to the RX path, or vice versa. Or if this is like mostly similar, then you need space on both. So what what is the strategy here? What can you, how you should approach this? So first, it's with memory optimization from the application point of view. It's always like you don't want to spend a lot of time and not do any significant gains. So the first step is find the big spenders, figure out what's the biggest, what is eating up your memory budget, and focus on those. It does not matter if you optimize, if you spend an hour to optimize some stack that was twice as big, if you're only saving up, for example, 1K, but then you have an embed TLS with 50 or usually 80K, and it's only using up like 50K. It's easier to first optimize that if you can. You have to determine if you need them, and if you are basically, you're starting this for the first time, you might not know if you need it. So there is some research needed to figure out, do I actually need this thing that is inside? Can I completely remove it? Or if I cannot completely remove it, can I tune it down somehow? Many subsystems have constraint variants. I think you're all aware of this. So for example, logging you can enable minimal logging, so you can still have some logs with minimal features. Same goes for the shell. Similar goes for the asserts. And also additionally, some of the subsystems have additional features. If you don't need them, you turn them off. So yeah, decide what you can miss and what is mandatory to have for your application. Now, you have to, so you also have to, when you start tuning threads, heaps, memory slabs, anything that is like runtime dependent, you have to define what are your test conditions, what are your device workflows, and possible code paths that your device will take. So if you're going to be sending out data, you want to be sure that you are optimized it against its actual use case, or let's say the worst style of a use case. So for example, maybe your device is sending out data every 10 seconds, but at some particular moment it starts sending out data rapidly at 1 second intervals. You have to optimize for that. You don't know how the network stack might behave to that, if there are more network packets in the pipeline. So first would really be like first order estimation would be test against all possible or let's say the most critical code paths, and check the reports for the maximum values. Second estimation would be keep device running for several days. You're going to find a lot of more things than just, 10 minutes, half an hour at the bench. Third estimation, you have several devices in the field. You make sure that you are recording those statistics and that you're sending them back to the cloud and you're actually visualizing them. This tries to solve the problem with that you see some kind of a behavior with a few devices on your bench, but you're going to see a different kind of a behavior when the things start scaling and you suddenly have 100 devices in the field and only 3 of them are experiencing or showing these weird symptoms when thread stack usage suddenly goes a little bit up every time with time, or heap is going up a little bit of time, maybe you have a memory leak. So there's like observability. This is, even if you're not optimizing, this is a thing that you should be doing if you have multiple devices. Okay, so demo. So this is, I will come back to this later. So I have a Nordic board here. Sadly, it's modified, so I can only use RTT, not UART. So I want to first showcase the PON cover. I think that's a very interesting one to show. I think this should be just enough, or it shouldn't be. Then I guess we're going to do it that way. And this one. this should be fine. So it takes some time. It parses through the L file. It figures out what are the relationship between the functions. It tries to do the call stacks, and then it spins up this. So this is the initial screen that you see. So the symbols that are not located. Sorry, yeah, definitely bigger. Thank you. So immediately the symbols get thrown into two different spaces. So basically everything that is unknown that cannot be tied to a particular source file, which does not necessarily mean things from the libc. Like you can still have Zephyr code that will Zephyr symbols from the Zephyr tree, and they will end up here, and the rest of the stuff. So if we go to the home on the right side, so go through a few of the folders, my project, and yeah, so you can see how much on this basis, like how much my project is consuming, how much is in the how much memory is coming from the Zephyr, how much is coming from the NRF, a few of the modules. So I don't know, like we can take a look in the Zephyr, and yeah, you can see there's something is consuming 88 kilobytes in the drivers, 99 in modules. And yeah, you can really discover the things and go down and figure out, okay, what is consuming some space, a lot of space here. And once you come to the file levels, I don't know, let's go into the IP. Not sure what we'll find, but yeah. So at one point when you're on the file level, you're gonna have a split between the functions and the symbols that are there. And yeah, the symbol, like for example, we can see there's a management stack. It's 4,600 bytes. There are a few functions here. Interestingly, if you go into the functions, you're also going to see which functions get called by this function and which functions are calling this function. So for this particular one, event work handler none, because I think probably this is probably, yeah, it's passed as a pointer to the work item. So the pun cover did not pick it up. Here is some assembly, and yeah, below here here's the worst case stack usage. So this might be useful for somebody to look at to figure out, okay, what is going to be the worst case stack when I'm going to be at this point, at this function. From like a really far away, or like a view from the top, if we return back to the entry point, there's a button that shows all of the symbols. So this is the one that I find most useful to figure out where something, what are the big consumers. You can do that also with NM tool. There's a flag to sort it by size. But if you like a visual presentation, there's this one. So yeah, there's a lot of code here, and at some point there's gonna be variables. Yeah. Okay. So those are the symbols that take up the most space. I have to say, so this version of the Azure IoT Hub sample, this is not the original version, so it had to be slightly modified so I could actually analyze it. Few things is you add analysis tools. That's going to consume space. If you're already at 99 something flash, you're not going to be able to compile the binary. So you have to throw out some of the things to actually do this. Plus, if you have LTO enabled, a lot more symbols are going to end up in the unknown section. So if you can disable that and disable some other symbols. So for example, I don't think that asserts are here enabled, and that saves some of the flash space. So yeah, so there are several variables here that are taking a lot of space. On the top is the firmware patch for the NRF 7000. If you have external flash, you can put this on the external flash and not pay the price of the flash on the internal one. So I'm just basically gonna ignore this one. So you need it in any case. This is not something that you can just throw out, as far as I know. You can just decide from where you are using this, and you can put it on the external flash, and you can use the XIP function, and the code will use it directly from there. Then the next one is embed TLS heap. So that seems a lot. The device just uses SSID. I mean, it just connects to the network with the name of the network and password. So it's not, and it does. Okay, so it does authenticate to the Azure server. There are certificates, so this is why this is used. Yeah, but it seems a lot. Then the next three, I guess. Yeah, so we have the Wi-Fi memory pool, the system heap itself, and the control memory pool. And rest of the stuff are essentially stacks. So what we can say is, okay, we should definitely look into a few of those things. So if you don't, in the beginning, when I started looking at this, none of those things, I didn't know where they are, and you basically had to develop a few skills to figure out, okay, where they actually are. And after some time, you see the pattern. So like I mentioned, the K heap prefix, you will then know where they are or how to look for them. The main thing is you find a symbol, and then you have to figure out what is controlling the size of that symbol. And usually for some of the things, it will be very, very, very obvious. Like, for example, there's a management stack. So there's a K, you might note there's a K-config symbol for that. And you might note there's a symbol for controlling this memory pool because you've seen it in Project Conf. So if we go onto the device, so once you know that, you can locate the symbols with the tools that I showed. But if you want to do like some kind of a RAM analysis, runtime analysis of the RAM. Okay. So for example, there's gonna be, so I added a few things here. There's gonna be like a memory analysis. So I added a way to track the usage of the buffers where you allocate from where the net buffers are allocating from. The same goes for the Wi-Fi, and we can see how much is allocated, and we can adjust to that. There's also, for some reason it got disconnected. I can restart it later. There's also the command for the kernel heap, so you can see it here. There is also, so for the networking, there is also this command. So you can see how many network packets are. You can see how many of the net buffers are total and available. I added this column here, so I can say, okay, I have a lot of those things. I'm just gonna, I can just disable them. There's that. Is there anything else that I wanted to show here? Yeah, there's embed TLS, heap, and yeah. So for example, by default, 81 kilos was allocated for this. It's only using 50. That doesn't mean that you can set it to 51 because memory allocators are allocating memory in blocks of some certain sizes. So you need to, and they will allocate more than what you ask for usually. So you have to, for example, you say, okay, this is the number, maybe let's add 5K just to be sure. And you basically rinse and repeat that. Yeah, so everything, so there were several, let's say, optimization runs for this. I can show it here. So I have put all of those things into the sample YAML. So test case, so I could build it via the command line, and we can see that our original was constructed. So basically. I had to remove a few of the flags, so I made it easier for myself later to test. So asserts were enabled, LTO was enabled, MTO boot was enabled. For the analysis, none of those things were here, and there were a bunch of other options which enabled me to do the analysis. So embed TLS was enabled, the shell for it was enabled, the net statistical stuff was enabled, and so on. Now for the optimizations, so this run went through, I would say, through the optimizations of the heaps and the stacks, and there's an optimize.conf file here that basically a lot of those values were either set explicitly by the sample, or they were implicitly set by the system already. So a lot of those things could be dialed down. What we found somehow is that for some reason, if you disable the IPv6, not only you save the flash space, but you also connect faster. There is some issue with the DNS resolver. There is also, yeah, the second optimization. So none of those things touched the partition table of the sample. So if I should be able to show that. So something to consider. You might not always have this option, but for example, there in the original report, if you might have noticed that there are about 8 kilobytes that you could remove from the TFM and give it to the application. So this is a way that you can also get memory. You just increase it by stealing it from some other place. Naturally, you have to know that this is going to be enough for the other part. There is also, if you're optimizing flash usage, there are a few empty partitions here that are added by the partition manager by default to ensure that that SPU, so Secure Protection Unit, has proper alignment for the 53. I think it's 8 kilobytes. No, 16. It's 16. So those things ensure that the regions that needs to be the boundary between the non-secure and the secure, it's at 16 kilobytes. So if, for example, this is just empty, you could have more settings, for example, and squeeze this TFM by throwing out of the things and still watch out for the precision, for the alignment. One thing that is kind of interesting, even though we are not using the second core, we're still going to pay the price of 64 kilobytes that we're not going to be using at all if we are not using the Bluetooth. I tried to play around with this, and I did get to the point where I could remove that, but at the time this felt a little bit more hacking, and I would not say that this is like completely tested in the sense that there are probably a few things that you have to disable in the device tree, then just tell the partition manager not to include that section. So yeah, probably somebody from the Nordic can explain this better than I did. Yeah, so back to the slides. So our test conditions, arbitrarily chosen. So I was sending 1 kilobyte of data. It was just a hard-coded string 10 times every 20 seconds. And I was receiving 1 kilobyte data like sporadically. And CJSON was parsing it. The important part about the CJSON, it also consumes heap, currently set up to use it from the memory, from the system heap. So it probably, the system heap could be a little bit large, usage of the system heap could be a little bit larger, and therefore the whole RAM usage could be a little bit larger if I was actually sending 1 kilobyte of structured CJSON data that had to be parsed first before being sent. Yeah, so sending, receiving, I triggered a disconnection by removing the access point, and I didn't test FOTA, I didn't test directed methods, so, and very little of the CJSON was used. And that was that was kind of the results out of that. So the first line is the original, and yeah, 69 kilobytes of RAM in the end. Optimized one, so adjusting of the heaps and stacks, gave us a bit about twice as much, and the last one essentially gave us 8 kilobytes from that stolen space from TFM. Free flash, so the flash usage did not, let's say, increase, or free flash did not increase so significantly. I think the only major jump was due to the, so I have to say the last one is also so IPv6 was disabled and the asserts were brought down in the sense that messages were removed and only the location was retained. So if you get a assert, you will only get the file location and source line location, but not the whole message that is there. Still useful enough to debug what is actually happening. Or you can completely disable them. So that was kind of the space that I was searching for. Your application might be completely different. Even if you're using Azure IoT Hub, you would probably care about different things. Naturally, for us, we also have to test FOTA, so that is going to be impacting the numbers. Yeah. So what I have learned. So I learned how to find things in the Zephyr with the tools that I mentioned. As a general rule, I found out that flash usage is really it's hard feature bound, meaning if you want to use a feature, you will pay the flash price no matter what. The only way to remove the flash usage, you disable the feature. With RAM, it's a little bit more soft. Still, if you use a feature, the feature will require the RAM for it, but usually that is more tunable in the sense of a stack. Most of the subsystems use some kind of a stack. You might not need, the default setup and the default size might be too much for what you actually need, so you can tune that down. External flash and execute in place are essential, basically, for the NRF 7000. Like if you're doing STA applications, if you're doing scanning, just the Wi-Fi scanning, you can probably get by. But doing anything that, our use case really requires a lot. I don't think I mentioned that we are also trying to do Wi-Fi enterprise. So that's the host app itself will consume a lot of space as well. So execute in place in this sense is essential. The last one, so keep the heaps separate if you can, if you have a control over that. So what I mean by that is CJSON currently from the sample by default allocates from the system heap. If your system heap usage is really large and at the same time you're allocating something from the CJSON, there might be a conflict. So it might be okay to allocate something with the CJSON and then release it and then allocate something else. But if you don't have control of that, those things might overlap and the maximum usage will be high. So what you can do is you keep the heap separate. If you know that whatever data you're expected to parse fits at 8 kilobytes, you're never going to have problem due to the interference with some other heap. If your heaps are separate. If they are not, then you have to somehow prove to yourself that this is not going to happen. Yeah, so that's it. Just a quick shout out. Because we develop a lot of products with Zephyr, and through the years we basically compiled a catalog of various repos. So if you're interested in any of those contents, there's a lot of stuff going on there. Yeah, so just go to our webpage and look for IRNAS dash prefix. Yeah, that's all. Thank you. Any questions? Yeah. Yeah. No, I did not play with that. But yeah, like I assumed, like for the optimized version, it still had logging, it still had shell, so it's definitely not the minimum that you can go run through.
Because the purpose of it also is like during development, you want to be able to debug things and see it.
Yeah.
It's not supposed to be like in production, but yeah,
Yeah, yeah.
Zephyr had this approach that you can actually have this dictionary-based logging.
Okay.
And I think we were able to reduce it by 100K by just
Okay, okay.
we had a lot of loggings, but
Okay, this is definitely something that I will look into. Yeah, thank you.
thank you for that presentation.
Thank you. Yeah, they're in the back.
Did you see any, or are there like significant drawbacks with this thread analyzer? Or like, you
Uh-huh.
in front, kind of in the background and report?
Yeah, I mean, it does, I mean, no significant ones, but like, I don't know if you noticed, like there was like the suggested settings for by default were at some point, like I was running it like I said, run it at 5 seconds. So the default is 60, by the way. I mean, it depends on what the rest of the application is doing. It will require CPU time. It will do something, but this usage is really meant as a, like, I would say, like an eyeballing usage. If you're using actually this on the device, you can call an API and run this at the time when you know that there not much is going on elsewhere, right? Like if you're, I don't know, if you have a sensor that is supposed to be sampling all the time or with some pauses, yeah, you do the threat analysis in the pause and you should be okay.